We are working with measures of dispersion, which is how dispersed or how spread out the data is. One way to measure how spread out the data is the range. And in question 1, the first thing we want to find is the range, which you take the largest number. In this example here, it's 25, and you subtract the smallest number, and that's the range, the difference between the largest and the smallest. In this case, 25 minus 5, you would get an answer of 20. The next measure of dispersion we are looking at is the standard deviation, and it is more complex than the range. It takes every single data value into account, and because of that, it will be a better and more reliable measure of how dispersed, how spread out the data is compared to the range. So to calculate the standard deviation, I'm going to go into Excel to do it. You do not have to use Excel, but I'm going to show you some tips and tricks of why Excel is great for these types of calculations. You can also do this with pen and paper or with like any standard calculator. So here's our data, the 5 different numbers. The first thing for the standard deviation is we need to find the mean of those 5 numbers. So you add them all up, and you should get 60 for this example, and then you divide by 5, and that is a mean of 12. Now, here is where my first tip in Excel comes in. You can find an average of numbers in Excel just by typing equals average. And then after you've typed that, you would type an open parentheses, select the data with your mouse, you close the parentheses, and it finds the mean or the average for you instantly. So 12 is our mean. To find the standard deviation, to work the formula out, we involve every single number. So all of our data values here, we're going to take that value and subtract the mean from it. So 10 minus 12 gives you a negative 2. 9 minus the mean of 12 gives you a negative 3, and so on. Again, the power of Excel, I just did the cell reference A2, that's where my 10 is, and wrote minus 12. Now, I can then drag this corner right here, just drag it down, and Excel is smart and knows that now I'm talking about A3 because I wanted to copy that formula down. So 9 minus 12. And then I wanted to do A4, which was 5, the number 5 minus 12, and so on. So I just really had to type that formula in once and then drag it down, and I get all of those subtractions. Now you may notice that some of these are negative because the value was less than the mean. We have one of them that's positive because 25 is bigger than the mean. If you would actually add these all up, they're always going to add up to 0. To go forward with our calculation of the standard deviation, we are going to add up eventually, but before we do that, we need to square all of these results. So I'm going to take each of these values. So I'm going to take negative 2 and multiply it by itself, or square it. Well, so negative 2 raised to the second power, you can do that on a calculator. Here I'm doing C2 to reference that cell and square it. You get a 4. Again, I'm going to just drag that corner, and now I have, and the negative 3 squared gives me 9. The negative 7 squared gives me 49, and so on. I have all the numbers squared. Now I want to add those up. So I'm going to type equals sum, or you could just do 4 plus 9 plus 49, etc. on your calculator, add those 5 up, and you should get the sum. So I'm going to write sum of the squares there. That's, in this example, it's 232. And now you want to divide by 1 less than our sample size. So this problem doesn't explicitly state that we're working with a sample of data. If you have the entire population, you divide by the number of pieces of data you have, which in this case would be 5. But whenever we have a small amount of data like this, and it's not really said whether it's the population or a sample, we can safely assume that it's a sample because it's such a small number of data values, just 5. So we're assuming it's a sample. We want to find the sample standard deviation. To do that, we need to take our result and divide by 1 less than the sample size. In this case, it's 4. All right, so divide by 1 less than sample size. And that's because we're finding the sample standard deviation we divide by 1 less. And the final thing you want to do on a calculator, or here in Excel, it's equals SQRT for the square root. And I'm going to do the square root of 58 there. And I get my result. I want to round it to the 2 decimal spots, the nearest hundredth, so I would get 7.62. And so that's my sample standard deviation. After I take that square root, I have my sample standard deviation. And the last thing I want to show you in Excel, just how great of a tool Excel can be, equals STDEV for standard deviation. And then since I want to find the sample standard deviation, I want to do STDEV.S for sample standard deviation. If I did .P, it would be if I have the entire population of data. But .S, and then I just select however large my sample is. Here it's those 5 data values. I close my parentheses, and I get that same result without going through all the steps of finding the mean, subtracting each individual value, squaring each individual value, adding them up, dividing, taking the square root. I let Excel do all that work behind the scenes, and I just have to know the right formula to type in for the sample standard deviation. For number 2, we have a random sample of 6 people, asking them how much money they have on them to the nearest dollar. And here is the results of our sample. We are again going to look at the range and standard deviation like we did in problem 1. The range, you find the largest value and subtract away the smallest value. For these numbers here, it would be 60 minus 4. And so our numbers range from 60 to 4. That's a range of $56. So that's one measure of how dispersed, how spread out our data is. For the standard deviation, I'm again going to do this in Excel, but you can do it on a calculator or just pen and paper. You have your 6 data values. You would add them all up, divide by 6. That gives you the mean. You can also do equals average for the mean here in Excel. Take each data value, subtract it from the mean, and you get a result. These should all add up to 0. If you would sum all these together, you'll get 0. How far away each data value is from the mean, and then square those results. So 0 squared, 30 squared, and so on. You get all the squared results. Next, you want to add all those squared terms up, and then divide by 1 less than our sample size, because we're finding the sample standard deviation, because we're working with a sample of data. We had 6 people we asked in this question, so we want to divide by 5. So I'm taking that number, dividing by 5, and then finally take the square root of your result to get the sample standard deviation. The shortcut in Excel is equals STDEV for standard deviation .S, because we have the sample standard deviation, and just select your data values. And now if we close our parentheses, we get our sample standard deviation. So that's the value we want, rounded to the nearest cent, which is 2 decimal spots. Part B says to add $15 to each value we have up here and see what the new range and the new standard deviation is. So let's just do that up here. I'm going to create a new column of data and just add 15. So 15 plus 30 is 45. If I drag this down, Excel will be smart and know that I wanted to add 15 to each of them. So you can see each of these values is 15 bigger. Let's just do the shortcut here and see what we get for our result for standard deviation. Our sample standard deviation of these new values is the exact same thing. So think about that. And it should make sense because we're measuring how dispersed, how spread out these data values are from one another. Well, if we've shifted every single one of them 15 larger, then compared to one another, they're not spread out any more than they were before. They're just all moved the exact same amount forward by $15. You're going to notice that the range stays exactly the same as well because the smallest value got $15 bigger. But the largest value also got $15 bigger. So now we have 75 as our largest, minus 19. as our new smallest, but that gives us the same result of 56 for our range. For number 3, our sample is these 5 data values in this example, and we're going to start off by finding the mean and standard deviation. I'm going to just do this in Excel. The mean, you add them all up and divide by how many there are. You can also use the equals average, select your data, and that is your mean. The standard deviation, you can watch the first part of this video if you want to see how to work it out by hand. But for sample standard deviation, you can just use that formula in Excel. And there is our sample standard deviation, rounded to 2 decimal places. Now for this problem, we want to see how the mean, which is a measure of the middle of the data, also the standard deviation, which is a measure of how dispersed or spread out the data is, we want to see how those values are affected when we change the data values by a fixed amount. So we're going to add 20 to each number up here. All right. So I'm going to say equals A1 plus 20. So each data value here, just make it 20 bigger. And when I drag that down, Excel makes each of them 20 bigger. And so let's look at our new mean and our new standard deviation. I'll do it over here to the side, the average of these new values. Notice it got 20 bigger. We took every data value, made it 20 bigger, the mean shifted 20 larger. So the center of the data moves 20 larger when you make every data value 20 larger, but how spread out the data is stays exactly the same because it's not any more spread out. These numbers aren't any more spread out from one another than these numbers are. So it's still dispersed just the same amount, even though the mean is shifted. In C, we're actually subtracting 5 from the original data values. Make sure you go back to the original. So here A1 minus 5 would be 8. And then I want to do that for all my data values, take 5 away from them. So let's find our new average, add them all up, divide by how many you have. In this case, I'm getting 8. So if I move every data value down 5 less, the mean moves 5 less. So we're kind of seeing that same pattern. It's making sense that the center of the data shifts with the data, but how spread out the data is, how spread out it is, the standard deviation is not changing if we shift every data value by the same amount. And that's what we want to talk about in part D here for our conclusions. What's about the change in the mean? If each piece of data is increased or decreased, the mean increases by that exact amount or decreases by that exact amount. For the standard deviation, it remains the same if each piece of data is increased or decreased by a specific amount. So now part E. You could work with these numbers in Excel, find the mean and standard deviation, and do the same with these numbers. But let's look for the pattern here, and you can solve this a little bit quicker. These numbers are all in order, 6 through 12. And notice these numbers are all exactly 580 bigger. So 6 plus 580 is 586. 7 plus 580 is 587, and so on. So you might have slightly different numbers in the problem you're working through, but look for that pattern. So I do need to find the mean and the standard deviation for one set of these numbers. Let's do it for 6 through 12. I could come into Excel, and let's find our average here for our data values. We're getting 9, and our sample standard deviation for those data values as well. And I get 2.16. So I could write that in for that first set of numbers. I could do it again here, but I don't really need to. From what I learned in parts A through D here, since these numbers are all 580 more than my original set, I know the mean is going to be shifted up by 580. And I know that since we had a consistent shift of all the data, the standard deviation remains the same because the data is dispersed or spread out exactly the same way it was in our original set. For number 4, try to solve this without doing any calculations. look at your two data sets and see which one is spread out more. The one that's spread out more dispersed, has a larger standard deviation. The one that's clustered closer together will have a smaller standard deviation. So looking at this one, it only goes from 13 to 16. All the numbers are very close to each other. It's going to have a smaller standard deviation than these values, which are more dispersed, all the way from 12 up to 23. So this first set will have a greater standard deviation. The data values that we have here are more spread out than we have in our second set. For number 5, our scenario here is an automotive service company that has two different franchises, and we're going to compare a sample data from both of those stores, the East store and the West store. So first we'll start off with a frequency distribution. So what you want to do here is we have our different classes already created for us, and we need to fill in how many data values fall within each of the classes. So how many data values from the East store are in the range 15 to 19? So you need to look through every single row and column here, and there's one value in that range, so I put a 1 in my frequency distribution. How many data values are in the 20 to 24 range? I do the same thing, and there's two values, the 20 and the 24, so I put a 2 there. Now this can be challenging to try to do on a computer because it's much more helpful if you can cross numbers out as you go through them. I encourage you to write these in Word or Excel or on a piece of paper or print this or something so that when you get the 15, you could go here and cross it out or somehow mark that you've counted that one. That way, when you reach the end, you should have every single data value crossed out or marked, and to make sure you haven't overlooked any or that you don't double count something. So it can be very helpful to do that. You can also double check why all these values should add up to 25 because we have 20, our sample size is 25 different days. Do it for the East store, then you have to do a frequency distribution for the West store as well. And then we're going to draw histograms. Now your histogram, the bottom axis here, our horizontal axis, is already set up for us, and we have the size of our bars. It should match up to the frequency distribution. The size of each bar comes from the frequency distribution. So for our East store, the first bar should have a height of a height of 1, and then we see a height of 2, and then 3, then 2, then 4, and so on. So that's what we see here, a height of 1, and then 2, then 3, then 2, then 4, and so on. The same thing with the West store. Find the heights of the bars that match what numbers you have in your frequency distribution. That would be the correct histogram. Using the histogram, first we want to see which store appears to have a greater mean, or do they appear about the same. So looking at our West store here, most of the data seems to be pretty close to 40. The tallest histogram bars are right there by 40. There's some a little less, some a little more. So I'm going to say that the average is probably in this 40 range. But I'm also going to say the same exact thing for my other histogram because I have, again, most of the tallest bars are right here by 40. But then there seems to be about the same less than that and about the same more than that. So when I average them all together, I'm imagining I'll get something close to 40. So just off appearances, I can't tell if they're exactly the same, but they do appear to be approximately the same from those histograms. So now I'm actually going to, for part D, I'm actually going to look at the histograms again and see if one of the stores appears to have greater standard deviation. So my West store here, the tallest bars are by 40, but there's just a few extra bars on either side, and they're kind of shorter compared to the bulk of the data. So it's not very spread out, the data isn't, and definitely less spread out than I'm seeing in this histogram. In this histogram, I have some tall bars by 40, but then there's quite a few larger, and there's quite a few smaller tapering off each way. So the data is more dispersed, more spread out. I anticipate a much higher standard deviation from the East store than I will see from the West store. In part E, I actually want to calculate those. And this can be another great reason, not just to create your frequency distributions, but also to use Excel for the average and sample standard deviation. Because With 25 data values, that's a lot to type into a calculator. Add up 25 data values, divide by 25, but equals average. Then you select your data, close your parentheses, and you get the average. Let me do that again with my West store equals average. And you can see this is much faster than typing in 25 data values and dividing by 25. So here is the averages. They actually are exactly the same. They both come out to the same number I will type in, and that is consistent with what I was anticipating here in part C by looking at my histogram. For the sample standard deviation, you definitely want to be using Excel or some type of software because this would be a lot to try to work out by hand. I'm getting this from my East store equals stdev.s. For my West store. And remember, I anticipated it being smaller in my West store, and it is quite a bit smaller. This one's almost twice as big, this number is, for the East store compared to the West store. So type those values in, round them correctly, and again, these values are consistent with what I was anticipating when I looked at the histograms in Part D. For number 6, our data is 5 heights. As for my example, it's the heights of the starting 5 on the women's basketball team. So this is a sample of the women from the basketball team. So when I'm finding the standard deviation, I want to do the sample standard deviation. I have these data values equals stdev.s, select my data value, and Excel will give me back the sample standard deviation, which gives me a measurement of how spread out the heights are for those 5 women.